All right, so what we were doing is we've done the first isomorphism theorem, which is our big nuclear letter. We use it to show the second isomorphism theorem. I want to restate the third isomorphism theorem. Let N be a normal subgroup of G. Then there's a one-to-one correspondence between normal subgroups of G containing N and normal subgroups of G mod N. Also, if bars and H is normal in G, we're also assuming that N is normal. It's a blanket assumption here. Then H mod N is normal in G mod N and G mod N mod H mod N is isomorphic G mod H. So here's what we did last time. So one-to-one correspondence between H with H between N and G. And subgroups of G mod N. So what we accomplished, we didn't finish the group last time, but what we did accomplish this, we showed that there's a one-to-one correspondence between subgroups of subgroups of G that contain N, call it H, and subgroups of G mod N. The way the correspondence worked was this way. Take your subgroup H, it corresponds to H mod N, which we showed actually was a subgroup of G mod N. We also showed if you have an arbitrary subgroup of G mod N, it is of this form, right? So any subgroup of this actually has to be of the form H mod N, where H is a subgroup, and that's the way the correspondence works in the other direction. So we've got this statement, first statement without the normals. What I want to do now is I want to show that this holds up when I apply the adjective normal. That is to say, if you have a normal subgroup of G containing N, then that gives you a normal subgroup here and vice versa. Right? Well, so let's look into that. Now suppose now suppose that this group in the middle, this H that falls between N and G, suppose it happens to be normal. Our goal is we need to show H mod n is normal in G mod n. Right? That's our main goal here. So to this end, let's suppose little h n is in H mod n and G n is in G mod n. So to show that this thing is normal in this, we need to take an arbitrary element and conjugate it and show that it's still in there. So consider the conjugate Gn inverse Hn Gn. So what happens when I conjugate this coset? Well, the first thing I'm going to notice is this thing is actually G inverse n H n G n. Agree? Because the inverse of Gn is G inverse n. Right? And these are all cosets, and the way I multiply this is just one big G inverse Hg n. Well, what do we know about G inverse Gn or G inverse Hg? But G inverse Hg is in H, right? Because H is normal at G. So this thing is in H mod n because this coset representative lives in H. So H mod n is normal in G mod n. So what we've shown is if this intermediate group happens to be normal, then the corresponding group over here is normal. Right. Now let's show that it works the other way, right? What if I pick a normal subgroup of G mod n, right? So let's explore that. A is normal in G mod n. So here I write A because it's just abstractly it's a subgroup. But from what I learned last time, I know something. I know that A is of this form. For some, that's the correspondence theorem we already did. So if I walk up to you on the street and I say, hey, I've got a subgroup of G mod n, you know that it has to take on this form. It has to be of some H mod n where H contains n and it's contained in G. It's an intermediate group. I agree with it. Now, what I really want to do is I want to show that H is normal in G. That's my goal. And then I will have the normal part of the statement taken care of. Okay. So, how are we going to do that? Well, I want to show that H is normal in G, so let's let H be in H and G be in G. And again, parenthetically, I'll write, we need to show that H inverse GH actually, G inverse HG is actually still in H. All right. If I can show this, then that will show that H is normal. Everybody with me? And what tool do I have? Well, the tool I have is that this thing is normal in G mod n. So here's what I do know. that I know that H mod n is normal in G mod n. I'll throw that in there to kind of tie it together. H mod n is normal in G mod n. So when I take the coset for G and the coset for H, and I conjugate this thing here by the coset, I should get something in H mod n, right? Well, let me do a little prestidigitation to this. Just like before, this is G inverse n, H n, G n, which is G inverse H G n. And this is in H mod n. Everybody agree with that? And this is just enough to leverage what I need. Because what does this mean? This means that whoops, let me not write this. I wrote that wrong. That's actually in some coset there. That's a better way to write that. Since this coset is equal to a coset, that means G inverse HG is in one of these cosets here. Therefore, G inverse HG is equal to H prime N for some H prime and H and N and N. But notice that N is contained in H. So both of these things here, H prime and N, are both in H. So that's in H. Therefore, G inverse HG is contained in H, and so H is normal in G. And so it works the other way. Okay, any questions on that? Questions so far? Yes.
The first line, I understand all the way up on this side of the board up until the bottom, but then when you go from that step to this step,
Here to here?
from the bottom one to the top. Yeah.
Let me put in some. This is in HN. That means that G inverse HGN is of the form HN, H prime N. Because it's got to be, this coset has got to be an H coset, right? And that'll give me the rest of what I want, because this means that notice that these are two sets, right? Now the identity is in N. So G inverse HG is in here. And this set is the same as this, so it's in H prime. Now pick it up here. Does that make sense? Other questions? Okay. So here's what we've got. we've got the second sentence, right? So now, then there's a one-to-one correspondence between subgroups of G containing N and subgroups of G mod N. We've also got that with the adjective normal applied. That is, there's a one-to-one correspondence between the normal subgroups of G containing N and the normal subgroups of G mod N. So let's totally try to conquer this, right? If H is an intermediate normal subgroup, then, okay, we've already proven this. First part anyway. What we have done H mod N normal mod N. So when we tackle this last statement, we know that if H is an intermediate group and it's normal at G, then this quotient is normal at G mod N. That was one of the things we proved with correspondence a moment ago, right? Now, how are we going to get this last part? This looks like death on a hot plate, doesn't it? Right? Because you've got cosets of cosets. It's like a bad scene from Caligula, right? I mean, let's try to do something that makes this a little bit better, right? How about this? Once again, I'm going to use my friendly neighborhood first isomorphism theorem, I think. Let me define the following homomorphism. And I want to be careful about this. I'm going to define the homomorphism this way. So my input is a coset. And you know, you all have heard me screaming about how I hate doing things with cosets, right? But this one's not going to be too bad. Okay, my input is a coset out of G mod N. I want my output, it's going to be a coset here, so it's got to be blank H. Please be easy on me. What's the easiest thing? Easiest coset. How about G itself, right? Always a good rule of thumb in math is to be lazy. So let's do that. What's the first thing I have to worry about this map? This, maps that get worked this whole time. Is this or is this not well defined, right? Because I've got my old problem. You might have the coset Gn, I might have the coset G prime N. We got to make sure they get the same answer. But this one's actually going to be pretty easy to see. We're going to tackle this one right away. Need to show B is well defined. So let's do that. Suppose Gn is equal to G prime. Actually, you know what? I'm going to change the notation here because it'll probably be easier for y'all to read. How about this? Xn equals yn. Suppose I have two of the same cosets. What I need to do is show you might represent the coset with X, I might represent with the coset Y. So what you're going to get when you do this function is you're going to get the coset XH. I'm going to get the coset YH. They better be the same thing. Otherwise, this isn't a function. It doesn't make sense. Everybody with me on them? So what does this mean for these two cosets? Anybody remember what this means? What does it mean for the coset Xn equal Yn?
Y inverse X is in A.
Good. Everybody remember that? But what do I know about the relationship between N and H N is contained in H, right? So if Y inverse X is in N, which is in H, then Y inverse X actually lives in H, which means so it's well defined. If you plug your X in, if you plug in your X in and get XH, and I take my Y in and get YH, we've gotten the same answers, right? So that the well-defined here wasn't too difficult. Everybody okay with that? Yes.
So here you're using the fact that y inverse x is in H to justify the fact that both x and y are in H, and that's
No, X and Y, no, no, that's not the case. So what this means, these two cosets means, as you said, that Y inverse X is in N, right? But if Y inverse X is in N, then they're in the bigger H, right? So Y inverse X is actually in H. And that means that these two cosets are the same with the bigger H attached, right? Because if I'd asked you in the first place, what does it mean for these two cosets to be the same? You would have said Y inverse X is in H. Right? Does that make sense? Yes.
So, wait, okay, so our goal was to show that XH equals YH?
That is correct.
Okay.
Right, because I've got XH and I plug it in and I get this answer. Or I'm sorry, I take X in and plug it in and I get XH. You take the same coset YN and you get YH. Now you and I plugged in the same things, even though they look different in the way they were represented, right? You might say 1/2, I might say 2/4. They look different in the way they were represented. You got output XH and I got output YH, which were the same thing. So it's good. It's good to go. Makes sense. Everybody agree with that? Okay. It's all downhill from here. The well-definedness is always the worst, I think. Okay, next task. Is this a homomorphism? That's not going to be too bad, I think, because if you look at phi of xn times yn, this is phi of xy, and by definition. And this, my friends, is xyh. And I can write that up again. And this is phi of x, phi of y. Up. Did not write that well. This is phi of x in phi of y. So this is a homomorphism. Totally conquered that. So I've got that it is. What else is true about this homomorphism? So this is well defined. It's a homomorphism. What other sexy property does this phi have? It's got one other nice property.
It's 1:1.
No, but take the flip side of that. It is onto, as a matter of fact, right? So let's see why it's onto. What does a typical element of this look like?
50% G in field.
Let GH be an element of G mod H. Well, certainly I can cover that by GH is phi of GN. Just take whatever that G is, and there you go. So this is onto. Okay, so yes,
I was following you, but how does that conclude that it's onto?
because any element of G mod H can be written in this form, right? And so to cover this arbitrary element, all I have to do is just go phi of Gn is GH, and then I've covered an arbitrary element, right?
So when you're considering the order of a set in the form something mod something, the order of that, because my concern was that the order of n could be smaller than h, but we mainly care about the order of g because g is defining the individual.
That's right. I mean, all you need is the coset representative, and we already know that this is a well-defined function, right? So, given an arbitrary coset here, it's the image of this one here. In fact, since n is smaller than g, I expect this in a certain sense to be bigger, because notice that h contains a, but dividing out. So let me give you an example. Would you agree that Z mod 4, so that is would you agree that all the integers that are multiples of 4 is a proper subset of all the integers that are multiples of 2, right? So multiples of 4 smaller than the multiples of 2. So multiples of 4, right? Every fourth one, h multiples of 2 every second one. Z mod 4z has 4 elements in it. Z mod the smaller, Z mod the bigger 2z has only 2 elements in it, right? And so it kind of, there's a role reversal there, right? What's the kernel of this? B is the set of cosets such that B of Gn, which is GH, is equal to right? So it's the set of all cosets that this map takes to the identity, which is the set of all cosets right? Because notice if G is in H, then this cosets the identity. And on the other hand, if this is equal to the identity, that means E inverse G has to be in H, which means that G has to be in H. And this is precisely H mod n, because it's all cosets of the form Hn, where H is in H. So by the first isomorphism theorem, so once again, we have the looming mushroom cloud of the first isomorphism theorem is, in our language, G mod n modulo the kernel of phi is isomorphic to the image of phi. Translating that for this particular thing that we went through, the kernel of phi was H mod n, and the image of phi, since it was all onto, is G mod H. That concludes the third isomorphism theorem. So, are there any questions on it? Any questions? Okay, so this is more or less where the material ends for the first exam, which is Friday. I'm going to go on into the next section on symmetric and alternating groups. I already expect you to know some things about the symmetric groups, right? How many elements does Sn have in it if n is finite? N factorial, what is Sn? It's the set of bijections from a set of n things to n things, blah, blah, blah. But we're going to learn some more groovy properties of the symmetric and alternating groups, and they are very, very important Because one of the big, so I will remind you of this definition here. Symmetric. So even though this is new, I've already done some of this that I expect you to know, so this will probably help as a bit of a review. Let me start off by reminding you what the symmetric group is. Definition 441. Let's suppose that A is a set, not empty. Let A be a non-empty set. Then SA is the set of F from A to A, such that F is bijective. One to one and on to. We have seen SA is a group under function composition. And that's why you need it to be bijective, right? In particular, when you compose two functions from A to A, you get a new function from A to A. That's good to go. If you have three functions and you're doing this FGH from A to A, then that function composition is associative. That's old 3190 stuff. There's certainly an identity always, right? The identity function from A to A just takes everything in A to itself. That's the identity function. But you only get inverses if it's bijective, right? And so that's the magic that makes this a group here. If the set A consists of the numbers 1, 2, 3, up to n, we write Sn or SH. That's a symmetric group on, sometimes people say on n letters. Notice that the number of bijections from a set of n things to itself is in fact 4. Let's look at an example here. One of the reasons that we study the symmetric groups, we're going to have a big theorem later where we use group actions, and we're going to show that actually, in a certain sense, I'm being a bit facetious here, but in a certain sense, if you understand the symmetric groups, you should understand every group, right? Again, that's a little fast and loose. And the reason I say that is it's going to turn out, we're going to discover that if you have any group, I don't care what it is, any group, it exists as a subgroup of some, this is called the, I gave you a definition, I didn't even tell you what to call it. This is called the symmetric group. On set A. Sometimes it's called the set of the group of permutations on the set A. Sometimes it's called, but it's just bijective maps. It turns out that if you have any group, you can realize it as a subgroup of a symmetric group for some set A. And in fact, if you have a finite group, which are very interesting objects of study, if you have a finite group, it sits inside some finite Sn, some n. And I'll give you a good example. This is probably a good review here. And this will help us with our computations that we should know. Find D6 as a subgroup of S6. Now, how many elements does S6 have? A lot, 6 factorial. It's got like 720. How many elements does D6 have? Just 12, right? It's the symmetries of the hexagon, right? Let me draw it. I'll draw it this way. It's easier for me to draw a hexagon this way, I guess. Okay, one thing that I can do to that hexagon is I can rotate it clockwise by however many 60 degrees, right? What permutation of these set of these 6 numbers do I get if I rotate it 60 degrees clockwise? If I rotate this 60 degree clockwise, where will 1 go?
The current position of 2.
1 will go to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 6, and 6 goes back to 1. Everybody okay with that? What happens if I flip this around the y-axis? What's the S here? What happens if I flip it this way?
1 and 4 go to themselves, 2 goes to 6, 3 goes to 5.
That's right. 1 and 4 are left alone. And 2 and 6 change places. And 3 and 5 change places. And that rotation and that flip, all you need are words made of the rotation and the flip, and you can get all 12 rearrangements of this. Notice that, let me give you an example here. S6 is much bigger. In S6, you can swap anything any way you want, right? For example, an element of S6 would be the function that leaves 1, 2, 3, and 4 alone and swaps 5 and 6. You can do that in S6 because that's a bijection. 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, 5 goes to 5 goes to 6, and 6 goes to 5. Everybody agree with that? Somebody explain to me why you can't do that here. Why you can't do this with the rigid hexagon.
Set dimensions.
You would, you'd have to rip it, right? The only way that you're going to swap these two and leave this alone is to like take a stapler and staple these 3 down, and then you're going to rip your hexagon out trying to swap these 2, right? So that's why there's many, many more elements of S6 than there are here. But let me give you what do you expect this to be? What happened in the dihedral group? When you flip, rotate and flip, remember what happens? Yeah, it goes backwards, right? It's the same thing as doing this. And you can see that in action here. We've done a similar one here with the pentagon, but I think this is worth seeing again. If you do, and this is good practice to our multiplication here, let's do SRS. That is 2, 6, 3, 5, 1, 2, 3, 4, 5, 6, 2, 6, 3, 5. Let's do this computation. Now, when I do these computations, I like to start at 1 and just be an accountant and make sure I account for everything and get it all done. But here, just for the sake of demonstration, I'm going to actually start at 6. It doesn't matter where you start, as long as you're complete about it. Where does 6 go? Yeah, now remember, go from this to this, right, 5 is correct. 6 goes to 2, which jumps to 3. jumps to 5, and then it's done, right? Okay, then where does 5 go? That is correct. 5 goes to 3, 4, and then it's done. 4. Yep, I think so. 4 goes to 5. No, 4 is up to here. 4 goes to 5 and then to 3. How about 3?
2.
Good. 3 goes to 5, jumps to 6, no 6, and then to 2. 2 then?
1.
2 goes to 6, then it jumps to 1 and it's done. Now, 1 better go to 6, otherwise I've screwed up somehow, but it's always good to check. See where 1 goes. It goes to 2 and then 6. It's good. Notice this is rotating that hexagon backwards, right? Counterclockwise. Right? And so you see that I took this group here and I realized it as a subgroup of S6. This isn't, I'm going to give you a theorem that shows that any group sits inside of the appropriate symmetric group, but sometimes it's not very economical. Okay, any questions on that? Any questions? Okay, so I'm going to give you a couple of theorems here. So I've used this terminology, but I'm going to formalize it here. Definition. Let sigma be A1 up to AM. That's it. A1, A2, AM, S, N. And let me give you some caveats here. AI is not equal to AJ. If I is not equal to J, that is to say these numbers in here are all different. And M is less than or equal to N. Then sigma is called a cycle of length and sometimes of order M. So sometimes we might call this an M cycle because it's a single cycle, right? There's a single group of numbers in parentheses and no repetitions here. If M equals 2, then this is called, it's often referred to as a transposition. Well, a transposition looks like this. A transposition actually turns out to be important. Basically, what a transposition is it's a function that only swaps 2 things and leaves everything else alone. Right. So let me ask you a question. Let me ask you all a question just for fun. How many of you play cards? Ever play cards, right? If you take a standard pack of 52 cards and you shuffle the heck out of it until it's random, can you get it back? You remember how when you buy a deck of cards, right? It goes ace through king. You know, you get it out of the pack and it's brand new. It goes ace through king of spades and ace through king of hearts and so forth and so on, right? Can you get from a shuffled pack back to the original pristine ace through king, ace through king, ace through king, ace through king, just by swapping 2 cards at a time? You can do your 2 swaps as many times as you want, but can you get back to the original pristine state just swapping 2 cards at a time? Yes, you can. Can you describe how you would do it?
You can find the ace of whatever the first suite is and swap it with the first card in the deck, and then do the same thing with the next card with the second card of the deck.
Eating process, right? So what you do is you start, look at the first card on the top. If it's the ace of spades, you're good to go. If it's probably not, then find the ace of spades in the deck and just swap it in position with that card. So now you got the ace of spades on top. So now you got the first card on. Look at the second card. If it's the king of spades, you're good to go, right? Or whichever one comes next. If it's the king of spades, you're good to go. If not, find the king of spades in the deck and swap it. Continue that process and exhaust it out. There's a theorem to this nature. Theorem, every element of SE so sigma here is an element of Sn. It's not necessarily a cycle. It's any element of Sn. Can be written. One has a product of disjoint cycles. So I mean cycles like we have above here, right? Cycles like this that are disjoint. So there's no overlap in the numbers between all the cycles, right? And this actually is unique. Unique up to rearranging the cycles. Two, as a product of transpositions. This second part of the theorem basically says what I said about the deck of cards. This basically says you can get any rearrangement on a standard pack of 52 cards by just swapping 2 cards at a time, if you're patient enough to go through the entire process. Now, I am going to finish today. We're going to come back and explore this one in a moment or afterwards, but I'm going to give you this definition. Notice for the second one, I did not say I could do it uniquely, because in general I can't. Let me give you this definition here. Let sigma be an Sn. We say sigma is odd if sigma is a product of an odd number of transpositions. And we say sigma is even if sigma is a product of an even number of transpositions. Okay, somebody be super critical and criticize my definition here. What's one perhaps alarm bell that might go off?
What's the product of infinite transpositions?
Okay, so, well, there's that. But I'm going to assume that you've got an element of Sn, so only finite. What's one thing that you might criticize or question at this point? You might question if my definition makes any sense in the first freaking place. Because how do you know that this is a well-defined definition? How do you know that somewhere in the depths of some Stephen King novel, there's some element of Sn, some big function that's one-to-one and onto, that you can write one way as a product of an odd number of transpositions by doing an odd number of swaps, but you could also in some other clever way get it by doing an even number of swaps. It's not clear, is it? I mean, suppose I've got some crazy rearrangement. I might have been able to do that by swapping things an odd number of times and also an even number of times. It turns out that can't happen. And this is really kind of an amazing theorem, and we're going to see why that's true later. Any questions? All right, folks, I will see you folks on Friday. I hope I see you this afternoon.